Right now, the inner core of Earth is growing 1 millimeter per year, and that slow crystallization is what powers the magnetic field keeping you alive. Subscribe if you want more of the cosmos. This is white space. Settle in, today we are not reaching outward. We are not pointing telescopes at distant galaxies or tracing the paths of light from stars that burned out 1 billion years ago. Today we turn inward, to the planet beneath your feet. To the ground that holds every city ever built, every grave ever dug, every root system ever grown. We are going to look at what this planet is, how it moves, why it moves, and where it is going. Not over the next century, over the next billion years, the surface of Earth looks permanent. From any given street corner, the horizon appears fixed, the mountains stable, the continents obviously and irrevocably where they are. But this appearance is one of the more persistent illusions in nature. What we call solid ground is the uppermost skin of a restless machine, one that has been operating without pause for 4.5 billion years and shows no sign of stopping. Every mountain range that impresses us today is a temporary scar. Every ocean basin is a feature that will be rearranged. Every coastline we have ever mapped will eventually be somewhere else, or submerged, or lifted into the interior of a continent that does not yet exist. To understand where Earth is going, we first need to understand what it is made of. And that requires going inside, which turns out to be a surprisingly difficult problem. The innermost layers of Earth are as inaccessible to us as the surfaces of distant planets. We have sent spacecraft to Venus, Mars, Jupiter, Saturn, and beyond. We have placed instruments on the Moon, on Mars, on asteroid Ryugu, on the nucleus of comet 67P. We have imaged the event horizon of a black hole 40 million light years away. We have never directly sampled anything deeper than about 12 kilometers beneath our own feet. The deepest borehole ever drilled is the Kola super deep borehole on the Kola Peninsula in Russia, close to the Finnish border. Work began in 1970 and continued for 24 years. At its deepest point, the borehole reached 12,262 meters, roughly 12 kilometers. This is the record for vertical drilling depth, and it is likely to remain so for some time, because the project was abandoned, not for lack of ambition, but because the rock at that depth was hotter than expected, exceeding 180 degrees Celsius, causing the drill bit to behave as if it were operating in a semi-liquid medium. Mechanical failure became unavoidable. 12 kilometers sounds impressive. It is not. The distance from Earth's surface to its center is approximately 6,371 kilometers. The Kola borehole penetrated less than 0.2% of that distance. It did not reach the bottom of the continental crust, which in that region extends to approximately 35 kilometers depth. In relative terms, drilling the Kola borehole on a model of Earth the size of a standard classroom globe would be equivalent to making a scratch in the paint with a pin. And yet science has not been stopped by this barrier. The interior of Earth has been mapped with remarkable precision through indirect means, and the picture that has emerged is detailed, coherent, and in many respects astonishing. The primary tool is seismology, the study of how seismic waves propagate through planetary interiors. When an earthquake occurs, it releases energy as waves that travel outward through the planet in all directions. These waves come in different types. Primary waves, or P waves, are compressional. They compress and expand rock in the direction of travel, and they can pass through both solid and liquid material. Secondary waves, or S waves, are shear waves. They displace rock perpendicular to the direction of travel, and they cannot travel through liquids because liquids cannot sustain shear stress. When a large earthquake occurs somewhere in the world, every seismometer on the planet records its arrival. The pattern of which stations receive which wave types, and how quickly and with what distortion, encodes information about every boundary and every compositional gradient the waves have passed through on their journey from source to receiver. Different materials transmit seismic waves at different speeds. Dense, stiff rock accelerates them. Less rigid material slows them. Boundaries between materials of different density refract the waves, bending their paths exactly as light bends when it passes from air into water. And when a wave encounters a liquid layer, its waves stop entirely. By deploying seismometers at hundreds of stations distributed across the globe and recording the arrival patterns and travel times of waves from earthquakes occurring anywhere on Earth, geophysicists have constructed three-dimensional models of the planet's internal velocity structure with a resolution that continues to improve as computing power increases and as the global seismometer network grows denser. The geometry of where waves are detected and where they are absent reveals the locations and properties of internal boundaries as clearly as a CT scan reveals internal structure in a living body. Supplementing seismology are several other methodologies. Gravimetric surveys measure subtle variations in the gravitational pull of Earth at different locations, variations that reflect differences in the density of subsurface rock. Over a buried iron-rich body, the gravitational pull is very slightly stronger than over a region of lighter granite. These signals are tiny, detectable only with highly sensitive instruments. But systematic surveys have mapped the density structure of the crust and upper mantle in considerable detail. Paleomagnetism studies the orientation of magnetic minerals locked into ancient rock layers at the moment of their formation, preserving a record of how Earth's magnetic field has shifted over geological time. Deep drilling, while physically limited in depth, extracts rock cores that provide direct samples of composition and temperature at depth, calibrating the indirect seismic and gravitational models. Xenolith analysis, the study of fragments of deep mantle rock that get carried upward inside erupting magma, provides direct, if fragmentary samples from regions otherwise inaccessible. Kimberlite pipes, vertical columns of volcanic rock that erupt with explosive violence and carry material from depths of up to 200 kilometers, have brought up chunks of the upper mantle and in some cases fragments of the transition zone encased in diamonds that protected them from alteration during their rapid ascent. Even meteorites are informative. Iron-nickel meteorites, thought to be fragments of the differentiated cores of disrupted asteroids, provide a compositional reference point for Earth's own core from outside the planet entirely. What this converging body of evidence has revealed is that Earth is structured in concentric layers, each with distinct composition, density, temperature, and mechanical properties. The outermost layer is the crust. On the continents, it is typically between 30 and 70 kilometers thick, though it can reach nearly 90 kilometers beneath major mountain ranges, where two plates have collided and stacked the crust into a thick pile. Continental crust is composed primarily of relatively low-density rock granite and its relatives rich in silicon, aluminum, potassium, and sodium. These rocks are ancient, chemically refined by billions of years of magmatic processing, and less dense than the material beneath them. The oldest surviving fragments of continental crust, the cratons that form the stable cores of continents, are over 3 billion years old. The Akasta gneiss of northern Canada, exposed in the Northwest Territories, has been dated to 4.02 billion years ago, making it the oldest known intact rock body on Earth's surface. Zircon crystals recovered from the Jack Hills of Western Australia contain mineral inclusions and chemical compositions recording conditions from 4.4 billion years ago, close to the age of the solar system itself, and preserving a chemical memory of Earth's earliest crust. Beneath the oceans, the crust is thinner, averaging around 7 kilometers, and is denser, dominated by basalt, dark iron, and magnesium-rich volcanic rock extruded directly from the mantle at mid-ocean ridge systems. The chemical difference between continental and oceanic crust is fundamental to the operation of plate tectonics, because the density difference is what determines which type of crust sinks when two plates converge. Below the crust lies the mantle extending nearly 2,900 kilometers downward. The mantle is by far the largest of Earth's internal layers, accounting for approximately 84% of the planet's total volume and about 68% of its total mass. It is composed primarily of silicate minerals, rock built around chains and networks of silicon and oxygen atoms bonded to varying amounts of magnesium, iron, calcium, and aluminum. The most abundant minerals in the upper mantle are olivine and pyroxene. Olivine, which gives the mantle its characteristic greenish tint in the rare cases where samples reach the surface, is a magnesium-iron silicate that is stable at moderate pressures, but transforms into denser crystal structures as pressure increases with depth. These transformations do not change the chemical composition of the rock. The atoms are the same, but they rearrange the crystal structure into more compact configurations, increasing the density. This progressive densification is what gives the mantle its layered seismic velocity structure. The mantle is solid. This point is frequently misunderstood, and the misunderstanding matters. On the timescale of seconds to hours, the timescale of seismic waves, the mantle behaves as a rigid solid, as waves propagate through it without difficulty, which proves it cannot be liquid. But on the timescale of millions of years, under sustained elevated temperature and pressure, rock deforms and flows without fracturing in a process called solid-state creep. A thick slab of mantle rock, subjected to the conditions of the deep earth and given enough time, will slowly change shape, rising where it is hotter, sinking where it is cooler, deforming around obstacles. The viscosity of the mantle is estimated at between 10 to the 20 and 10 to the 23 Pascal seconds, depending on depth, numbers that are difficult to intuit but correspond to a material that, for practical purposes at geological timescales, behaves as an extremely thick fluid. The temperature within the mantle increases with depth from around 1000 degrees Celsius at the base of the crust to approximately 3700 degrees Celsius at the boundary with the core. These temperature differences drive convection, slow, churning circulation currents that rise where rock is hotter and sink where it is cooler. Hot mantle rock rises toward the base of the plates over millions of years. As it ascends, the decreasing pressure allows partial melting, and the melt migrates upward to erupt at mid-ocean ridges or at hotspot volcanoes. Cool, dense rock sinks at subduction zones, dragging the overlying plate downward. This circulation is the engine of plate tectonics. At the boundary between the upper and lower mantle, at around 410 to 660 kilometers depth, the increasing pressure forces olivine to reorganize its crystal structure. At 410 kilometers, olivine transforms to wapsleite. At 520 kilometers, wapsleite transforms to ringwoodite. At 660 kilometers, ringwoodite breaks down into a mixture of bridgmanite and ferropericlase in the lower mantle. These phase transitions have important geophysical consequences. The density jumps at these boundaries produce the seismic discontinuities that define the transition zone, and the crystal structures of wapsleite and ringwoodite, unlike olivine, can accommodate significant amounts of water stored as hydroxyl ions within their lattice, not as liquid water, but as chemical bonds, invisible and inert, except under the extreme pressure and temperature of the transition zone. The total amount of water stored in this way across the global transition zone may equal several times the volume of all the world's surface oceans. Earth may be a much wetter planet than its surface suggests, with the bulk of its water inventory locked into the crystal structure of rock 400 to 700 kilometers below the surface. Beneath the transition zone lies the lower mantle, extending from 660 kilometers to 2,900 kilometers depth. Here, Bridgmanite, the most abundant mineral on Earth by volume, yet only identified and named in 2014 because it cannot survive the pressure reduction accompanying any sample brought to the surface, constitutes the dominant rock-forming mineral. The lower mantle is thought to be more viscous than the upper mantle, though by how much is debated. Its convection is slower, its circulation cells larger. At the very base of the lower mantle, in a region designated the D layer, the rock comes into contact with the liquid iron of the outer core above it. This boundary is the most extreme interface on Earth, a transition from dense silicate rock at approximately 3,700 degrees Celsius to liquid metal at around 4,000 degrees, across a chemical boundary of fundamental importance. Large, anomalously slow regions in the D layer called ultra-low velocity zones are interpreted as regions of partial melting or extreme compositional variation, possibly representing remnants of ancient subducted oceanic crust that has sunk through the entire mantle over billions of years. Rising plumes of unusually hot material from this boundary are believed to generate hotspot volcanism at the surface. The Hawaiian Islands, Iceland, the Kerguelen Plateau, the Afar region of Ethiopia, eruptions occurring far from plate boundaries, driven by columns of anomalously hot mantle material ascending from the deepest part of the convecting mantle. Below the mantle lies the core, divided into two distinct regions. The outer core, extending from roughly 2,900 kilometers to 5,100 kilometers depth, is a liquid composed primarily of iron and nickel, with a density deficit relative to pure iron, suggesting the presence of lighter alloying elements, most likely sulfur, oxygen, silicon, or some combination, though the exact composition remains an area of active research and debate. The temperature in the outer core ranges from approximately 4,000 degrees Celsius at its upper boundary to around 5,000 degrees at the boundary with the inner core. At these temperatures, iron would be liquid at surface pressure, but the lower mantle above is solid because the pressure there is sufficient to force silicate minerals into a solid phase. The outer core is liquid because the pressure, while enormous, is not yet sufficient to force iron itself into a solid phase at these temperatures. That threshold requires the additional weight of the entire overlying mantle, which is only achieved at the inner core boundary. The motion of this liquid iron, driven by the heat escaping upward from the crystallizing inner core boundary and by the chemical buoyancy created as lighter elements are expelled during crystallization, produces the convection that generates Earth's magnetic field. Electrically conducting liquid iron moving through an existing magnetic field induces electric currents, which reinforce the magnetic field, a self-sustaining feedback process called the geodynamo. For the geodynamo to operate, the planet must rotate, and Earth's rotation at 1,675 kilometers per hour at the equator is sufficient to produce the Coriolis forces that organize the convection into the helical flow patterns needed for field generation. The field produced is broadly dipolar, resembling the field of a bar magnet, but it is far from simple at Earth's surface. The field has significant non-dipole components that shift over decades. The magnetic poles wander. The North Magnetic Pole has been moving from northern Canada towards Siberia at an accelerating rate over the past century, having traveled more than 1,000 kilometers since systematic measurement began. The field's overall intensity fluctuates over centuries. And periodically, on average, every few 100,000 years, though with enormous variability, the polarity reverses entirely, with the process of reversal taking a few thousand years and passing through complex transitional states that are poorly understood. During reversals, the field weakens substantially, potentially to 10 or 20% of its normal strength, which may have consequences for surface radiation exposure. The inner core is a solid sphere approximately 1,200 kilometers in radius, composed of iron crystallized under pressures exceeding 3 million atmospheres. Despite the extreme temperature estimated at roughly 5,000 to 6,000 degrees Celsius, comparable to the surface of the Sun, the iron is forced into a solid phase by the crushing weight of the entire planet above it. The inner core is not perfectly uniform. Seismic waves travel through it faster along Earth's rotation axis than perpendicular to it, indicating that the iron crystals are preferentially aligned. It also appears to contain a further subdivision, an innermost inner core roughly 500 kilometers in radius, with a different crystal orientation, which may record a transition in the style of inner core growth early in its history. The inner core grows by approximately 1 millimeter per year as liquid iron at the outer inner core boundary crystallizes. This releases latent heat, the heat of solidification, which rises into the outer core and drives its convection, which sustains the geodynamo. It is a self-reinforcing planetary engine. The cooling and solidification of the core powers the magnetic field that protects the surface. At its current growth rate, the inner core will require approximately 90 billion years to solidify completely, far beyond the remaining lifespan of the Sun. What connects all of these interior layers to the surface of Earth, to the mountains, oceans, earthquakes, and volcanoes, is the theory of plate tectonics. The idea that continents move has a surprisingly difficult history. For centuries, observers noted that the coastlines of continents, separated by ocean, seemed to fit together like fragments of a broken object. Francis Bacon noted the similarity of the Atlantic coastlines in 1620. Antonio Snider Pellegrini produced an explicit continental reconstruction showing the fit in 1858. But these observations remained curiosities rather than science because no physical mechanism could be proposed. The geology of the early 20th century was dominated by the theory that mountains formed by the slow contraction of a cooling Earth. As the planet lost heat, the surface was thought to wrinkle like the skin of a drying apple. In the early 20th century, the German meteorologist and geophysicist Alfred Wegener assembled a systematic case for continental drift that went far beyond the geometric fit of coastlines. He documented the remarkable similarity of fossil organisms on continents now separated by thousands of kilometers of ocean. The Permian plant Glossopteris appeared in rock formations across South America, Africa, India, Australia, and Antarctica, land masses that make no biological sense as separate provinces unless they were once connected. Glossopteris seeds are too large and dense to have been carried by wind across open ocean. The freshwater reptile Mesosaurus, a small Permian creature about a meter long, appears in equivalent rock formations in both Brazil and Gabon. It cannot have crossed an open ocean. Lystrosaurus, a pig-sized plant-eating reptile that was the dominant land vertebrate in the early Triassic period, has been found in Antarctica, India, South Africa, and Russia, a distribution that makes no sense if these were always separate continents. Wegener also pointed to geological evidence. The Appalachian Mountains of eastern North America traced along their structural trend and then continued across the Atlantic, aligned precisely with the Caledonides of Scotland, Norway, and Greenland. These mountain belts were built in the same ancient collision event, between 400 and 500 million years ago, and were then separated when the Atlantic opened. The match is not approximate, it is structural and compositional. Wegener concluded that approximately 250 million years ago, all of Earth's land masses were assembled into a single supercontinent he called Pangaea, from the Greek for all Earth. He proposed that Pangaea had begun to split apart around 200 million years ago with its northern region, Laurasia, comprising the future North America, Europe and Asia, separating from its southern region Gondwana, comprising the future South America, Africa, India, Australia and Antarctica. Wegener's hypothesis was largely dismissed during his lifetime. The problem was mechanism. His proposed driving force, centrifugal force from Earth's rotation, acting on the lighter granite of the continents, was quickly shown by physicists to be orders of magnitude too weak to move a continent. Without the mechanism, the hypothesis remained scientifically unacceptable. Wegener died in Greenland in 1930, and the confirmation of his central insight came only decades later. The breakthrough came through oceanography. During the late 1950s and into the 1960s, systematic magnetic surveys of the ocean floor revealed a consistent and striking pattern. The oceanic crust on either side of the mid-ocean ridges was magnetized in alternating bands of normal and reversed polarity, arranged in symmetric stripes about the ridge axis. The interpretation was that new oceanic crust was continuously forming at the ridge, recording the direction of Earth's magnetic field at the time of solidification, and then spreading symmetrically away from the ridge as new material was added. This seafloor spreading, proposed by Harry Hess in 1960 and confirmed by the magnetic stripe evidence interpreted by Vine, Matthews and Morley, provided the mechanism Wegener lacked. The continents are embedded in large, rigid plates that include both oceanic and continental crust. These plates move as integrated units driven by metal convection, by the pull of dense subducting slabs, and by the push of new material at spreading ridges. The evidence from earthquake distributions confirmed the picture. When global maps of earthquake epicenters were plotted, they concentrated into the narrow linear belts that mark plate boundaries, belts that correspond precisely to the geological features of mid-ocean ridges, subduction trenches, and transform faults. The precision of this correspondence was so striking that once seen, it made the plate boundary map appear almost self-evident. There are three fundamental types of plate boundary. At divergent boundaries, plates move apart. The mid-ocean ridge system, 70,000 kilometers of continuous underwater mountain range running through every ocean basin, is the primary expression of global divergence. At the ridge crest, the seafloor is actively splitting. Magma arises from the decompressing mantle, erupts as basalt pillar lavas on the ocean floor, and solidifies into new oceanic crust. The ridge is hydrothermally active, riddled with black smokers and white smokers, hydrothermal vents that spew superheated mineral-rich water into the cold, deep ocean, supporting communities of chemolithotrophic organisms that derive energy from the chemical disequilibrium between the hot vent fluids and the cold seawater without any dependence on sunlight. These vent ecosystems, discovered only in 1977 by the submersible Alvin at the Galapagos Rift, were among the most paradigm-shifting discoveries in biology of the 20th century, demonstrating for the first time that life did not require sunlight as a primary energy source. Divergence also occurs on land. The East African Rift system stretches several thousand kilometers from the Afar Triangle in Ethiopia through the vast lakes of the East African Rift: Turkana, Albert, Edward, Kivu, Tanganyika, Malawi, to the Mozambique Channel. Here, the African plate is being pulled apart. The Rift Valley floor has dropped relative to the surrounding plateau along a series of normal faults. Lake Tanganyika, already the world's second deepest lake at over 1,400 meters, is deepening. The Red Sea represents a more advanced stage. What began as a continental rift has widened into a young ocean as Arabia separated from Africa over the past 20 to 30 million years. It continues to widen at roughly 1 to 2 centimeters per year. Given tens of millions of years more, Eastern Africa will separate entirely from the main continent, and a new ocean will open where today there is Rift Valley. At convergent boundaries, plates approach each other. When oceanic crust meets continental crust, the denser oceanic plate descends beneath the lighter continental material in a process called subduction. The descending plate flexes downward at the subduction zone, forming a deep ocean trench. The Peru-Chile Trench, running along the western coast of South America, reaches over 8 kilometers depth and is the surface expression of the Nazca Plate descending beneath the South American continent. As the plate descends, it carries with it water and other volatile compounds stored in hydrated minerals. At depth, these volatiles are expelled by the increasing temperature and pressure. Released water dramatically lowers the melting point of the overlying mantle wedge, generating magma that rises through the overriding plate and erupts at the surface. The Andes, stretching the full length of South America, are the volcanic and structural consequence of this subduction. The Cascades of the Pacific Northwest, including Mount Rainier, Mount Hood, and Mount St. Helens, represent the same process where the Juan de Fuca Plate subducts beneath North America. Subduction also generates the largest earthquakes on Earth. The 1960 Valdivia earthquake off southern Chile, the largest instrumentally recorded, had a magnitude of 9.5. The 2011 Tohoku earthquake, magnitude 9.1, lifted the Japanese seafloor by several meters and generated the tsunami that overwhelmed the Fukushima Daiichi nuclear plant. These megathrust earthquakes are not rare exceptions, they are the regular expected consequences of the stress accumulation and release that characterizes all locked subduction zones. When two continental plates converge, neither sinks easily. Continental crust is too buoyant. The collision instead compresses and thickens the crust, building mountain ranges. The Himalayas record India's ongoing collision with Asia began approximately 50 million years ago. India continues to press northward at 5 centimeters per year, and Mount Everest grows by approximately 4 millimeters per year as a consequence. The Alps record an older but still active collision between Africa and Eurasia. Africa moves northward at nearly 2 centimeters per year, and the Mediterranean, a remnant of the ancient Tethys Ocean, is being consumed. In approximately 50 million years, the basin is projected to close, replaced by a mountain range comparable in scale to the present Himalayas. At transform boundaries, plates slide past each other horizontally. The San Andreas Fault, 1,200 kilometers long, is the most studied continental example. The Pacific Plate moves northwestward relative to the North American Plate. Los Angeles sits on the Pacific Plate, San Francisco on the North American. The fault does not glide smoothly, different segments lock for decades to centuries, accumulating elastic strain, then release it suddenly as earthquakes. The 1906 San Francisco earthquake produced up to 6 meters of horizontal displacement along hundreds of kilometers of fault length in a matter of seconds. Magnitude 6 and larger events occur on the fault system on average roughly once every 2 decades. The recognition that plates move in predictable directions at measurable speeds, now directly confirmed by GPS geodesy, which detects plate velocities at the millimeter per year level from permanent stations around the world, allows both backward and forward modeling of Earth's surface configuration. Looking backward, before Pangaea was Rodinia, assembled approximately 1 billion years ago. Before Rodinia was Columbia, or Nuna, at around 1.8 billion years. Before Columbia, Kenorland at around 2.7 billion years, though the evidence for these earliest supercontinents is increasingly fragmentary because so little rock of that age survives. At least 5 complete supercontinent cycles can be identified in the geological record. Each lasting 300 to 600 million years, the cycle is consistent. A supercontinent forms as all continental crust assembles. The mantle's heat, unable to escape efficiently beneath the thick insulating crust, accumulates. Eventually, mantle plumes rise against the base of the supercontinent with enough force to fracture it. Rifts open, widen into seas, then into young oceans, then into mature ocean basins. The fragments disperse, subduction zones eventually close the new oceans, and the fragments reassemble, but in a different configuration because the geometry of where new subduction initiates is not predetermined. 250 million years from now, the current dispersal will reverse. Models disagree on geometry but agree on outcome. A new supercontinent will form. The Atlantic may close as new subduction initiates along its eastern margin, bringing the Americas back to Eurasia and Africa Pangaea Proxima. Or the Pacific may close first as the Americas drift westward to merge with Asia. Amasia, centered near the Arctic, the specific pathway depends on where and when new subduction zones develop, which is not fully predictable. But the tendency towards supercontinent assembly is driven by forces intrinsic to the mental circulation, and the outcome is not in serious doubt. The environmental consequences of the next supercontinent would be profound. Reduced subduction means reduced volcanic activity and reduced volcanic outgassing of carbon dioxide, the long-term carbon cycle in which CO2 released by volcanoes is consumed by silicate weathering and biological activity, and eventually returned to the mantle via subduction would be disrupted. Atmospheric carbon dioxide could gradually decline, cooling the climate. Simultaneously, the vast interior of a supercontinent would be remote from maritime moisture, creating desert conditions across enormous areas. The geological record of Pangaea supports both effects. Both the most extreme cold periods and the most extreme warm periods of the past 350 million years occurred during Pangaea's existence, suggesting a climate system driven to its limits by the supercontinent configuration. The climate of Earth is not simply a function of geology. It is a product of the interaction between the solid planet, its oceans, its atmosphere, and the energy it receives from the sun. A coupled system of extraordinary complexity with feedback loops operating on timescales from hours to millions of years. The fundamental engine of climate is solar radiation. The sun delivers energy to Earth in the form of shortwave radiation, primarily visible light. Approximately 30% of this incoming energy is immediately reflected back to space by clouds, aerosols, ice, snow, and other reflective surfaces. This fraction is Earth's albedo, and it is not constant. It changes with cloud cover, with ice extent, with aerosol loading from volcanic eruptions. The remaining 70% is absorbed by the surface and atmosphere, heating them. This absorbed energy is eventually returned to space as long-wave infrared radiation. In the global annual average, inflow and outflow are in approximate balance, which is why Earth's temperature is approximately constant on decadal timescales, rather than continuously rising or falling. The balance is maintained through a complex interplay of processes, among which the greenhouse effect is paramount. Water vapor, carbon dioxide, methane, nitrous oxide, and ozone absorb outgoing infrared radiation and re-emit it in all directions, including downward toward the surface. This warms the surface above the temperature it would have without an atmosphere. Without the greenhouse effect, Earth's global average surface temperature would be approximately negative 18 degrees Celsius. With it, the actual average is around positive 15 degrees. Life on Earth exists because of the greenhouse effect. The question is always one of calibration and of stability over time. Carbon dioxide is particularly important because, unlike water vapor, it does not condense and rain out of the atmosphere when its concentration changes. It accumulates, and it is tied to the long-term geological carbon cycle through silicate weathering. Atmospheric carbon dioxide dissolves in rainwater to form carbonic acid, which reacts with silicate rocks at the surface, converting them to carbonate minerals that are eventually carried to the ocean by rivers and deposited as limestone on the seafloor. This weathering process removes carbon dioxide from the atmosphere at a rate that depends on temperature. Warmer temperatures accelerate weathering, which draws down more carbon dioxide, which cools the planet. This negative feedback is one of Earth's primary long-term thermostat mechanisms, which has kept global temperatures within a range compatible with liquid water for most of the past 4 billion years, despite a 30% increase in solar luminosity over that period. One of the most significant sources of interannual climate variability is the El Niño Southern Oscillation System, a coupled interaction between the tropical Pacific Ocean and the overlying atmosphere. Under normal conditions, the trade winds blow westward across the equatorial Pacific, pushing warm surface water toward Asia and Australia. The western Pacific sea surface is typically 5 to 8 degrees Celsius warmer than the eastern Pacific. The temperature difference drives deep atmospheric convection over Indonesia and the maritime continent, producing the heavy rainfall that characterizes equatorial Southeast Asia. Meanwhile, along the coasts of Peru, Ecuador, and northern Chile, the surface wind stress drives cold, nutrient-rich water upward from depth. This upwelled water sustains enormous populations of anchovies, sardines, and the seabirds and marine mammals that feed on them, one of the world's most productive marine fisheries. Every 2 to 7 years, this pattern breaks down. The trade winds weaken. The warm water pool that had accumulated in the western Pacific spreads eastward along the equator. The thermocline, the boundary between the warm surface layer and cold deep water, deepens across the eastern Pacific, suppressing upwelling along the South American coast. The fish populations crash as their food supply collapses without the cold, nutrient-rich water from depth. The coastal fishermen of Peru have known this pattern for centuries. They named the warm phase El Niño, the Christ child, because it often arrived around Christmas. The atmospheric consequences extend far beyond the eastern Pacific. Rainfall shifts from Indonesia and northern Australia, which experience drought, to the central and eastern Pacific. The Indian monsoon weakens. Southern African rainfall decreases. Abnormal rainfall falls on coastal Peru and Ecuador, on southern Brazil, on the American Southwest. El Niño events have been associated with some of the most severe droughts and floods in modern history. The 1982 to 1983 event caused tens of billions of dollars in damage and thousands of deaths globally. The 1997 to 1998 event was the strongest of the 20th century and produced wildfires across Indonesia of a scale not seen since, releasing carbon dioxide that measurably affected global atmospheric CO2 concentrations for the following year. The monitoring of El Niño has become one of the most sophisticated operational forecasting systems in Earth science. A network of approximately 70 buoys deployed by the National Oceanic and Atmospheric Administration across the tropical Pacific continuously measures sea surface temperature, subsurface temperature profiles at multiple depths, wind speed and direction, humidity and ocean currents. These data stream in real time to research centers where they are assimilated into numerical models running on supercomputers. Forecasts of El Niño onset, peak intensity, and decay are routinely issued 6 to 12 months in advance, with skill levels that have improved substantially over the past 3 decades. These forecasts have genuine economic value. A reliable El Niño warning issued in advance allows farmers in Australia and Southern Africa to adjust crop choices, allows water management authorities to pre-position reservoir capacity, allows fisheries managers to protect stocks during the collapse period. La Niña is the opposite phase, a strengthening of the normal pattern, with stronger trade winds, cooler eastern Pacific sea surface temperatures, enhanced rainfall in the western Pacific and Indian Ocean, and drought in the eastern Pacific and parts of the Americas. The 2020 through early 2023 period saw an unusually prolonged La Niña event, lasting approximately 3.5 years rather than the typical 1 to 2 years. During this extended cold phase, global average surface temperatures were suppressed relative to the underlying warming trend. When the La Niña gave way and El Niño conditions developed in mid-2023, the stored heat was released into the climate system with remarkable speed. Combined with the ongoing anthropogenic warming trend, the result was a sequence of global temperature records that climatologists had projected, but that still arrived with startling abruptness. Climate models project that the coming decades will see continued warming regardless of the mesocycle. The range of outcomes depends primarily on the trajectory of greenhouse gas emissions. Under high emission scenarios, global average warming of 3 to 4 degrees Celsius above pre-industrial levels by 2100 is projected, with severe consequences for sea level, agriculture, and the habitability of tropical regions. Under aggressive mitigation, warming could be limited to 1.5 to 2 degrees. The physical difference in numbers seems small. The consequences are not. At 4 degrees of warming, large portions of the tropics experience wet bulb temperatures during summer heat events that exceed the physiological limit for human survival without cooling. Sea level rise of 1 to 2 meters by 2100 and several more meters by 2200 as ice sheets respond displaces hundreds of millions of people. Agricultural systems adapted to current climate regimes fail. The restructuring of where food can be grown and where people can live becomes one of the dominant geopolitical facts of the next century. The study of Earth's past climate has established that the planet has experienced far more dramatic changes than anything currently projected on the near-term human timescale. 55 million years ago, a rapid and severe warming event struck the planet, now known as the Paleocene-Eocene thermal maximum. Over a geologically brief interval of 5,000 to 20,000 years, global average surface temperatures rose by approximately 5 to 8 degrees Celsius. The deep ocean warmed by 4 to 5 degrees. The isotopic composition of carbon in ocean sediments shifted abruptly, recording a massive injection of isotopically light carbon, depleted in carbon-13 relative to carbon-12, indicating the carbon came from organic or biogenic sources rather than from volcanic rock. The carbon injected during the PETM has been estimated at between 1 and 5 trillion tons, comparable in magnitude, though spread over a longer interval, to the total that humanity could release from all recoverable fossil fuels. The cause is debated. The destabilization of methane hydrates, ice-like compounds trapping methane in seafloor sediments, is one leading hypothesis, because a warming trigger could cause hydrates to decompose and release methane, which is itself a potent greenhouse gas and oxidizes to carbon dioxide in the atmosphere, causing further warming in a runaway feedback. The initiation of large-scale volcanism associated with the opening of the North Atlantic as early Atlantic rifting generated massive flood basalt eruptions is another candidate mechanism. Both processes may have operated in sequence. The consequences were severe. Extinctions struck the deep ocean, particularly among foraminifera, the microscopic organisms whose calcite shells form the bulk of deep-sea sediment. As carbon dioxide dissolved into the ocean, it acidified the water and raised the depth at which calcite dissolves. Deep-sea carbonate sediments were replaced by non-carbonate clay layers across large areas of the ocean floor. This characteristic signature, the sudden replacement of carbonate-rich sediment by carbonate-poor clay, followed by gradual recovery, is what allows geologists to identify the PETM boundary in sediment cores taken from ocean drill sites around the world. The recovery of the climate system as the excess carbon was gradually drawn down by silicate weathering and organic carbon burial took approximately 200,000 years. Some researchers have noted that the PETM's carbon signature, rapid, massive, and isotopically light, shares abstract features with what a technological civilization burning fossil organic carbon would produce in the geological record. This observation, made in a scientific context and without any implication of a supernatural cause, led to a formal thought experiment known as the Silurian hypothesis, examined by astrophysicist Adam Frank and climate scientist Gavin Schmidt in a paper published in 2018. The hypothesis asks if a technologically advanced civilization had existed on Earth in the deep past and had then disappeared, would we be able to detect evidence of it today? The intuitive answer is yes, surely ruins, artifacts, or geological disturbances would be obvious. The careful answer is probably not. The geological record is far less forgiving of time than this intuition suggests. Consider what would remain of our own civilization after 10 million years of geological processing. The structures we build, cities, roads, airports, dams, cover less than 1% of Earth's land surface. They are built from materials that are, on geological timescales, chemically unstable. Steel corrodes, concrete dissolves slowly in acidic groundwater, glass devitrifies. Over 10 million years, plate tectonics would have moved some continental regions into collision zones or subduction trenches. Erosion would have stripped surface layers in many regions. The physical traces of a civilization, its buildings, its infrastructure, its vehicles, would be essentially gone, reduced to chemically altered mineral grains scattered through sedimentary layers. What might survive is a geochemical signature, just as our civilization is already producing a distinctive geochemical fingerprint in sediments. Elevated carbon dioxide with a depleted carbon-13 signature, nitrogen anomalies from industrial fertilizers, plutonium from nuclear testing, persistent synthetic organic compounds. A past industrial civilization might have left an analogous chemical anomaly. The PETM is the closest natural analog, a rapid carbon isotope excursion with a biological organic signature detectable in sediment cores 55 million years later. It does not require a previous industrial civilization. Its natural causes are adequate. But the PETM illustrates that the geological record can preserve geochemical signals from rapid, high-magnitude perturbations over tens of millions of years. The Silurian hypothesis does not argue that a previous civilization existed. It argues that we cannot confidently rule it out on the basis of not finding physical ruins, because we would not expect to find them. The absence of evidence in this case is not strong evidence of absence, because the preservation conditions for physical ruins over millions of years are so poor that we would not find them, even if they existed. Ancient rock formations in geologically stable regions offer the best windows into the deep past. The Pilbara Craton of northwestern Australia contains some of the oldest exposed rock sequences on Earth, with well-preserved sedimentary formations dating back 3.5 billion years. The Khazau Craton of South Africa preserves ancient rocks of similar age. The Superior Province of northern Canada exposes Archean crust spanning a vast area, some of it over 3 billion years old. These cratons are the fragments of the most ancient continental nuclei, those parts of the original protocontinental crust that survived the repeated processes of mountain building, subduction, and erosion that have recycled virtually everything else. Within them, the most ancient accessible geological record is preserved. In the Pilbara, layered structures interpreted as stromatolites, microbial mats, push evidence of life back to at least 3.5 billion years ago. In the Dresser Formation of the Pilbara, Carbon isotope anomalies in carbonate and organic carbon layers record the signatures of biological carbon cycling at a time when the Earth was barely 1 billion years old. The Kola super-deep borehole contributed its own insights into deep time preservation. At depths approaching 8 kilometers, the drilling crew encountered sedimentary rock, ancient ocean sediments, compressed and metamorphosed by burial but still recognizable as sedimentary in origin. Within this rock, embedded in organic microfossils preserved against the odds by the chemistry of their carbonaceous surroundings, were the mineralized remains of 24 species of ancient plankton. Their age exceeded 2 billion years. Despite temperatures exceeding 100 degrees Celsius and pressures thousands of times atmospheric, the organic compounds encasing these cells had maintained sufficient chemical integrity to allow species identification. The discovery demonstrated that the geological record can preserve biological information under conditions that seem intuitively hostile to preservation, which has direct implications for the search for ancient life on other planets. The borehole also produced geological surprises that forced revisions to existing models. Temperatures at depth were substantially higher than the pre-drilling predictions, a geothermal gradient that implied the base of the crust would be far hotter than expected. And that helped explain why the drill bit ultimately failed. The predicted boundary between granite and basalt, expected at around 7 kilometers based on seismic velocity models, was not the compositional boundary at all. The seismic velocity change reflected a metamorphic phase transition in the granite, not a change in rock type. And open fractures filled with highly saline water were found much deeper than expected, implying that the crust is permeable to fluid flow at depths previously assumed to be sealed by pressure, with implications for the transport of heat, dissolved minerals, and potentially even microbial life through the deep crust. These findings connect to one of the most significant discoveries of recent decades, the deep biosphere. For most of scientific history, life was assumed to require sunlight, oxygen, and moderate temperatures to be essentially a surface phenomenon. This assumption was overturned by the cumulative evidence from deep drilling programs, surveys of deep mines in South Africa and Scandinavia, and studies of deep groundwater systems around the world. Living organisms, bacteria, archaea, and in some environments fungi inhabit rock at depths of several kilometers at temperatures exceeding 70 to 80 degrees Celsius in complete darkness, with no dependence on photosynthesis or on any organic material produced at the surface. The total biomass of the deep biosphere is now estimated to be comparable in magnitude to the total biomass of all life at Earth's surface. The number of individual cells is staggering, approximately 10 to the power of 30, a number that exceeds the estimated number of stars in the observable universe. These organisms are metabolically active, but extraordinarily slowly by surface standards. Some deep subsurface bacteria are estimated to divide only once every 10,000 years. A single cellular generation, the time from one cell division to the next, may span a geological epoch by human standards, but the cell is alive, maintaining its membrane integrity, repairing molecular damage, processing chemical energy from the rock-water reactions around it. These organisms derive energy from chemolithotrophy, the extraction of chemical energy from reactions between rock minerals and groundwater that occur regardless of any biological input. Sulfate-reducing bacteria consume dissolved sulfate and organic compounds, releasing hydrogen sulfide. Iron-reducing organisms transfer electrons to iron oxides in the surrounding rock. Hydrogen-consuming microbes exploit the molecular hydrogen produced when water reacts with iron-bearing minerals in a process called serpentinization. a reaction that occurs wherever water percolates through olivine-rich mantle rock, producing hydrogen gas and heat, and representing a chemical energy source that has been available at depth since Earth first had liquid water. The implications for astrobiology are profound. Mars lost its surface habitability billions of years ago. Its magnetic field weakened, its atmosphere eroded, its liquid water disappeared to space or froze in the polar caps. The surface of Mars is almost certainly sterile, irradiated, dry, oxidizing, chemically hostile to organic molecules. But the subsurface of Mars is a different environment. Serpentinization reactions have been occurring on Mars throughout its geological history. The presence of olivine-bearing rocks detected from orbit confirms this. If life ever existed on early Mars, when the surface was warmer and wetter and the magnetic field intact, some lineages may have retreated into the subsurface as conditions deteriorated, just as deep subsurface life on Earth occupies niches that would be immediately fatal to surface organisms. Detecting this hypothetical Martian subsurface life requires drilling several kilometers into the Martian crust, a capability not possessed by any current mission, but the target of future exploration programs. Europa, Jupiter's second largest moon, presents a different case. Beneath its ice shell, approximately 15 to 25 kilometers thick, lies a global liquid water ocean, kept liquid by tidal heating from Jupiter's powerful gravity. The ocean floor is in contact with silicate rock, and tidal dissipation almost certainly drives hydrothermal activity at the seafloor. This configuration, liquid water, mineral rock, chemical energy from hydrothermal reactions, is precisely what supports the deep-sea hydrothermal vent ecosystems on Earth that were first discovered in 1977 and that are now known to support diverse communities of organisms entirely independent of sunlight. The Europa Clipper mission, launched in 2024, will characterize the Moon's ocean and ice shell in detail as a precursor to a possible future lander or cryobot that might eventually sample the ocean directly. Enceladus, Saturn's small moon, provides the most direct evidence yet of an active subsurface ocean in the outer solar system. Geysers near its south pole continuously vent water vapor, ice particles, and organic molecules into space. The Cassini spacecraft flew through these plumes repeatedly between 2005 and 2017 and directly sampled their composition. The plumes contain molecular hydrogen, the signature of active serpentinization in the rocky core, as well as complex organic molecules and silica nanoparticles characteristic of high-temperature hydrothermal reactions. Enceladus appears to have, in active operation right now, all the chemical conditions that we associate with the origin and sustenance of life on Earth. The question of whether intelligence is rare or common in the universe is, at some level, a geological and geochemical question as much as a biological or astronomical one. The record of what has happened on Earth, and potentially what is happening on other worlds, is written in rock, in ice, in sediment, in the chemistry of atmospheres. Reading that record correctly requires the same understanding of plate tectonics, mantle convection, the deep biosphere, and the climate system that we have been building over the past century. These are not separate sciences, they are aspects of a single planetary science applied to the broadest possible question: under what conditions do complex, organized systems arise, and for how long do they persist? Before we consider what future civilizations might find in the rock record, it is worth pausing on a question that the geological record itself raises. What would Earth have looked like if a different branch of life had continued its trajectory rather than being interrupted? 66 million years ago, an asteroid roughly 12 kilometers wide struck the shallow sea of what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear weapons. The immediate destruction was local. The secondary effects were global. Debris ejected into the upper atmosphere blocked sunlight for months to years. Photosynthesis collapsed, the food web that supported large animals disintegrated from the bottom up. The cold and darkness that followed the impact winter killed 3/4 of all species on Earth, including every non-avian dinosaur. The non-avian dinosaurs had been the dominant terrestrial vertebrates for 160 million years, more than twice as long as the time since their extinction. Their evolutionary history had produced extraordinary diversity. Enormous sauropods with necks 15 meters long, evolved to rich vegetation far above any competing herbivore, agile ceratopsians with elaborate cranial ornamentation suggesting complex social signaling, and theropods, the lineage that includes birds ranging from sparrow-sized Microraptor to Tyrannosaurus rex. Among the theropods, the trend toward larger relative brain size was measurable and documented through the Cretaceous. Some lineages, the Troodontids and Dromaeosaurids, had encephalization quotients approaching or exceeding those of modern birds, which are among the most cognitively capable non-primate vertebrates. Whether this trajectory would have eventually produced language, tool use, or abstract reasoning cannot be known. Evolution does not have predetermined destinations. But the direction was there. The small mammals and their relatives that shared the Mesozoic world with the dinosaurs occupied the marginal niches, mostly small, mostly nocturnal, mostly generalist. In a world without the mass extinction, they would likely have remained there, constrained by the ecological dominance of a highly successful, diverse group of large vertebrates. The specific trajectory that led over 66 million years from small rat-like creatures to primates to humans depended critically on the sudden opening of ecological space created by the asteroid. Without that opening, the path to intelligence through the mammalian lineage would have been blocked or at least substantially delayed. What the geological record tells us more generally is that the specific path to intelligence is sensitive to contingency. The conditions that existed at the end of the Cretaceous were producing increasing biological complexity, as every preceding interval of geological time had done. Somewhere in that trajectory, intelligence may have emerged in dinosaurs, in their successors, in something else entirely. But the specific timing and the specific lineage were not predetermined. They depended on a rock from space arriving at the wrong, or from our perspective, precisely the right moment. This leads naturally to the Silurian hypothesis, which takes this sensitivity to contingency seriously and asks over 4.5 billion years of Earth history, with complex life present for 600 million years and large-brained social vertebrates for tens of millions of years. What is the probability that our civilization is the only technological civilization this planet has ever produced? The answer, carefully examined, is that we do not know, and that the geological record as currently readable would not tell us even if the answer were no. The absence of ruins is not evidence of absence of civilization. It is evidence of the limits of geological preservation over millions of years. Ancient rock formations give us the best windows. The Pilbara Kraten of Australia, the Kap Vaal of South Africa, the Superior Province of Canada. These regions preserve the most ancient accessible records. Within them are not only the signatures of the earliest life, but the templates for understanding what long-duration preservation looks like in the geological record. A geochemical anomaly from a past technological civilization, a carbon isotope excursion, a nitrogen anomaly, a spike in certain trace metals, might exist in these rocks and be interpreted as natural variability. It might exist and not yet have been sampled, or it might have been recycled entirely into the mantle, leaving no accessible record. What we can say is that the geological record can preserve chemical signals over billions of years. The Kola borehole showed us that biological information can survive 2 billion years of deep burial. The PETM demonstrated that a rapid carbon injection from organic sources leaves a clear and interpretable signature over 55 million years. The tools for detecting such signals are becoming steadily more sensitive. And the motivation for looking? The recognition that Earth is not necessarily a first-time experiment in technological complexity is scientifically legitimate, even if the prior probability of a positive result is low. The question connects to the future as directly as it connects to the past. In approximately 250 million years, the next supercontinent will begin to assemble. By that time, whatever lineages of life survive the coming centuries of human modification of the biosphere will have had time, far more time than has elapsed since the Cambrian explosion, to diversify, adapt, and potentially evolve new forms of complexity. Whether any of those forms will be capable of asking the same questions we are asking now is unknowable. Whether our own descendants, biological or technological, will still be present in any form is equally uncertain. What the geological record tells us, however, with consistent clarity, is that change is the fundamental condition of this planet. Nothing about Earth's surface, its climate, its oceans, or its life is fixed on geological timescales. The features we treat as permanent, the continents, the atmosphere's composition, the locations of mountain ranges and ocean basins, are transient configurations in a continuous process of transformation. Understanding the mechanisms of that transformation is not merely an academic exercise, it is the only way to understand where we came from, what we are part of, and what we might reasonably expect from the future of this extraordinary, restless, and entirely unrepeatable world. Understanding the long-term future of Earth requires confronting a constraint that is often overlooked in discussions of climate change and geology. The Sun itself is not static. Stars evolve. The Sun has been fusing hydrogen into helium in its core for approximately 4.6 billion years. And as it does, the proportion of helium in the core gradually increases. Helium, being denser than hydrogen, contracts the core slightly. The contraction raises the temperature and pressure, which accelerates the fusion rate. The net result is that the Sun has been slowly but steadily brightening throughout its existence. At the time of Earth's formation, the Sun's luminosity was approximately 70% of its current value. Today it is 100%. In another billion years it will be approximately 10% brighter than it is now. In 5 billion years, it will have exhausted its core hydrogen, expanded dramatically into a red giant, and likely engulfed the inner planets. This gradual brightening has an immediate implication for Earth's habitability that is almost never discussed outside specialist literature. The planet is already approaching the inner edge of the Sun's habitable zone. The habitable zone, the range of distances from a star at which liquid water can exist on a planetary surface, moves outward as a star brightens. Earth currently sits comfortably within the habitable zone, but it is not stationary within it. As the Sun brightens, Earth's effective position within the zone drifts inward toward the hot inner boundary. Models suggest that in approximately 1 billion years, the Sun will be bright enough to trigger a catastrophic climate feedback on Earth. The mechanism is the water vapor feedback, or more specifically, a runaway version of it. Water vapor is the most powerful greenhouse gas in Earth's atmosphere. As surface temperatures increase, more water evaporates, which increases the water vapor content of the atmosphere, which traps more heat, which raises temperatures further, which evaporates more water. This is normally a bounded feedback. The increased water vapor also increases cloudiness, which increases albedo, which partially offsets the warming. But at a sufficiently high level of solar forcing, the feedback can become unbounded. absorbed solar radiation exceeds the maximum rate at which a planet can radiate heat to space, a limit set by the physics of a water vapor-saturated atmosphere. When this limit is breached, temperatures rise without bound until all surface water has evaporated. This is the runaway greenhouse effect, the process that is thought to have transformed Venus from a potentially habitable world to its current state of extreme heat, with surface temperatures of around 465 degrees Celsius. For Earth, the threshold for runaway greenhouse is estimated to be roughly 40% more solar irradiance than at present. The Sun will reach that level in approximately 5 to 7 billion years, but a slower, partial version of the process. A moist greenhouse may begin much sooner. Models developed by researchers including James Casting and James Hansen suggest that as solar luminosity increases over the next 1 to 2 billion years, stratospheric water vapor levels will increase, allowing ultraviolet photolysis to break water molecules apart. The liberated hydrogen is light enough to escape Earth's gravity and be lost to space. Over geological timescales, this process would gradually dehydrate the planet, not catastrophically, but inexorably. The oceans would not boil. They would slowly evaporate, and the water would be lost to space, molecule by molecule, over hundreds of millions of years. The timing of this process is sensitive to atmospheric composition and to feedbacks that are difficult to model precisely. But the broad trajectory is clear. Earth's surface habitability has an expiration date of approximately 1 billion years from now. This perspective reframes the significance of life's 4 billion year tenure on Earth. The origin of life, which occurred within the first few 100 million years of Earth's history, was extraordinarily early. The emergence of complex multicellular life, which happened only in the past 600 million years, was relatively recent, compressed into the latter part of Earth's habitable window. And the emergence of technological intelligence, which may be unique in Earth's history or may have precursors we cannot identify, is happening now, near the end of that window. We are, in a very real sense, a late-arriving species on a planet that may be passing its prime. This does not diminish what life has accomplished here or what it might yet accomplish, but it provides context. The geological record of Earth is not simply a neutral archive of past events. It is the record of a planet that has been extraordinarily hospitable to life for an unusually long time, and that is gradually approaching the limits of that hospitality. Understanding those limits, understanding the long-term carbon cycle, the water cycle, the role of the greenhouse effect, the trajectory of solar evolution is as important for understanding Earth's future as understanding plate tectonics or climate variability. The connection between the long-term carbon cycle and the Sun's evolution is subtle but crucial. Silicate weathering, the reaction between atmospheric carbon dioxide and surface rock that removes CO2 from the atmosphere, is temperature dependent. Warmer temperatures accelerate weathering, which draws down more carbon dioxide, which cools the climate, and negative feedback. This feedback has operated for billions of years as the Sun has brightened, keeping Earth's climate within the range compatible with liquid water, despite the steady increase in solar forcing. But the feedback has limits. As the Sun continues to brighten, the weathering thermostat must work harder, removing more and more atmospheric carbon dioxide to keep the surface cool. Eventually, in approximately 500 million to 800 million years, atmospheric carbon dioxide will be reduced below the threshold required to support C3 photosynthesis, the form of photosynthesis used by most plants. At that point, most terrestrial plants would die. The ecosystems they support would collapse. Only organisms capable of C4 photosynthesis, which can function at very low CO2 concentrations, would persist for a while longer. Another few 100 million years. Eventually, even that threshold would be crossed. Complex multicellular life on Earth's surface would end not because of an asteroid impact or a supervolcano, but because the Sun has been gradually turning up the heat for 5 billion years and the thermostat has finally run out of range. The deep biosphere, interestingly, would persist. Chemolithotrophs do not depend on photosynthesis, do not require CO2 as a carbon source in the same way, and can survive temperatures far above what surface life can tolerate. The deep subsurface of Earth might remain habitable in a minimal microbial sense for billions of years after the surface has become uninhabitable. Life began in the deep subsurface, or perhaps at hydrothermal vents, before it colonized the surface. It may end in the deep subsurface long after the surface has become uninhabitable. The story of life on Earth begins and ends in the dark. The timeline of Earth's geological future can be roughly sketched. In the next 10 million years, continued plate tectonic activity at rates comparable to today, the opening of the East African rift into a narrow sea, continued growth of the Himalayas, ongoing earthquakes and volcanism along all active plate boundaries. In the next 100 million years, significant rearrangement of continental positions, possible closure of the Mediterranean, continued northward movement of Australia into Southeast Asia. In the next 250 million years, formation of the next supercontinent, whatever its configuration will be. In the next 500 to 800 million years, decline of atmospheric carbon dioxide below the threshold for most photosynthesis, extinction of most surface plant life and the ecosystems it supports. In approximately 1 billion years, the onset of a moist greenhouse, beginning the long process of ocean loss as water vapor escapes to space. In approximately 1 to 2 billion years, Earth's surface becomes uninhabitable for complex life, though microbial life in the deep subsurface may persist. In approximately 5 billion years, the Sun exhausts its core hydrogen, expands into a red giant, and the inner solar system, including Earth, is consumed or severely altered. Against this timeline, human civilization occupies an almost infinitesimally small fraction of the available duration. We have existed for 10,000 years of complex organized society within a window of perhaps a billion years of remaining surface habitability. The ratio is 1 to 100,000. We have used less than 1% of the time available to us. What might be done with the remaining time by us, by our descendants, by whatever intelligence comes after, is a question that goes beyond geology. But geology provides the framework. The rock record tells us that this planet has supported life for nearly 4 billion years, that life has repeatedly diversified and adapted through catastrophic changes, that intelligence is a late development but not necessarily a unique one, and that the systems governing the planet's habitability, plate tectonics, the carbon cycle, the geodynamo, the greenhouse effect, are understandable in sufficient detail to anticipate their future trajectories. This understanding is itself extraordinary. For most of Earth's history, no organism had any awareness of the processes governing the planet's long-term evolution. The stromatolite-building microbes of the Archean were not aware that they were profoundly altering Earth's atmosphere by generating oxygen as a byproduct of photosynthesis. The trilobites of the Cambrian were not aware that they lived within a plate tectonic system. The dinosaurs were not aware of the asteroid's approach. We are the first organisms, as far as we know, who can read the rock record with sufficient precision to understand not just what happened, but why, and to extrapolate that understanding into the future with quantitative precision. This represents something genuinely new in the 4 billion year history of life on Earth, an organism that can model the planet's past, understand its present dynamics, and project its future trajectory across geological timescales. Whether that capacity translates into the ability to meaningfully influence those trajectories, to deflect asteroids, to manage the carbon cycle, to preserve habitability against the slow brightening of the sun, is an open question. The technology required for such interventions on a planetary scale does not yet exist and may never exist. But the understanding that makes such interventions conceivable already does exist, and it emerged from the same geological science that traces the movements of tectonic plates and the composition of Earth's interior. There is a deep irony in the timing. We have developed the capacity to understand Earth's geological future at precisely the moment when our own activities are the dominant driver of near-term geological change. The Anthropocene, the epoch in which human activity constitutes a geologically significant force, began approximately 300 years ago with the onset of industrial fossil fuel combustion. In that 300-year interval, we have altered the carbon cycle more rapidly than any natural process in the past 55 million years. We have caused the extinction of hundreds of species per year, a rate comparable to the mass extinctions of the geological past. We have produced novel minerals and chemical compounds that do not exist in nature and that will be preserved in the sedimentary record for millions of years. We have altered the nitrogen cycle through industrial fertilizer production, changed the chemistry of the ocean through carbon dioxide absorption, and left radioactive signatures of nuclear weapons testing in sediments from pole to pole. The Anthropocene layer will be detectable in the rock record millions of years from now. Future geologists of whatever species will see a sharp geochemical boundary marking a transition from the Holocene, with its relatively stable isotope ratios and biodiversity signatures, to a sudden interval of anomalous carbon, nitrogen and heavy metal concentrations, followed by a mass extinction signal in the fossil record, followed by whatever comes next. Whether that record will also show the recovery and continuation of complex life, or its absence depends on choices made in the near-term future. This is the lesson that geology teaches most insistently, if least comfortably. The rock record is not a story of inevitable progress. It is a story of change, sometimes gradual, sometimes catastrophic, in which the dominant organisms of each era eventually give way to something else. The something else is not predetermined. It emerges from the interaction of organism and environment, from the accidents of catastrophe and survival, from the slow accumulation of evolutionary change. Life persists. Specific forms do not we are one specific form. We are also apparently the first specific form with the capacity to read the record of all the forms that came before us and to understand, at least approximately, the forces that shaped their fates. Whether we use that understanding to improve our own odds of persistence, to manage the climate, protect biodiversity, reduce the risk of catastrophic conflict, and eventually expand beyond the surface of a single vulnerable planet, or whether we allow the short-term dynamics of economics and politics to overwhelm the long-term perspective that geology provides, is the central question of the current geological moment. The planet does not particularly care how we answer. Its tectonic engine will continue. The mantle will convect, the plates will move, the mountains will rise and be eroded, new ocean floor will form and be consumed. The supercontinent will assemble and break apart again, as it has done at least 5 times before. The deep biosphere will persist through all of it, metabolizing slowly in the dark. The sun will brighten, the oceans will eventually begin their long departure. All of this is written into the physics of the planet and the physics of the star, and it will proceed whether any conscious observer is present to note it or not. But right now, for this brief geological moment, there is an observer. There is a species that can read the record of 4.5 billion years and understand what it says, not perfectly, not completely, but with extraordinary and improving precision. That capacity is itself a geological fact. It emerged from the same processes that built the mountains and filled the oceans. It is made of the same atoms that cycle through rock and air and water. And it is by any reasonable measure one of the most remarkable things that has ever happened on this planet. The ground beneath us is not permanent. The sky above us is not fixed. The civilization we have built is fragile by geological standards. But the understanding we have accumulated of deep time, of the forces shaping and reshaping this world, is real, and it is ours to use. The geological record contains episodes of change so extreme that they challenge any intuition shaped by human timescales. Among the most dramatic is the series of events collectively known as Snowball Earth, a hypothesis now supported by substantial evidence that the entire surface of Earth was glaciated on at least 2 occasions during the Proterozoic era, between approximately 750 and 580 million years ago. The evidence for global glaciation comes from multiple independent lines of inquiry. Glacial deposits, rock types called diamictites, formed by the grinding and deposition of debris beneath glaciers, are found in rocks of the appropriate age on every continent, including in regions that were at tropical latitudes at the time of deposition as determined by paleomagnetism. The presence of glacial sediments at the equator implies either that the glaciation was truly global in extent or that the geological understanding of ancient continental positions is seriously wrong. Other lines of evidence support the global interpretation. The widespread presence of banded iron formations, a type of sedimentary rock that forms when iron dissolved in anoxic deep water is oxidized and precipitates, a process that requires the ocean to be chemically isolated from the atmosphere for long periods, and geochemical anomalies in carbonate rocks, immediately overlying the glacial sediments called cap carbonates, which record a rapid and extreme shift in ocean chemistry consistent with a sudden thaw. The mechanism proposed for Snowball Earth is a runaway ice albedo feedback. Ice and snow are highly reflective. Their albedo approaches 90% in some cases, meaning they reflect nearly all incident sunlight rather than absorbing it. If ice sheets expand sufficiently from the poles toward the equator, they increase Earth's overall albedo, which reduces the amount of solar energy absorbed by the planet, which cools the climate further, which causes more ice to form. This feedback is normally kept in check by the greenhouse effect, which provides a warming force that counteracts the ice albedo cooling. But if the greenhouse effect were somehow weakened, perhaps by a period of low volcanic activity and efficient carbon dioxide drawdown by silicate weathering, or by a change in continental configuration that altered ocean circulation, the ice albedo feedback could overcome the restoring force and drive the planet into a completely glaciated state. Once fully glaciated, the planet would be trapped. With the entire surface covered in highly reflective ice, almost no solar energy would be absorbed, and the planet would remain frozen regardless of its distance from the sun. The only escape from the snowball state was through the gradual accumulation of volcanic carbon dioxide in the atmosphere. Volcanoes continued to erupt throughout the snowball episodes, releasing CO2 as they always had. But during a global glaciation, the silicate weathering that normally removes CO2 from the atmosphere was drastically reduced, because most rock was covered by ice. With no weathering sink and continued volcanic outgassing, atmospheric CO2 gradually accumulated over millions of years until it reached a level sufficient to trigger a catastrophic greenhouse warming event. The ice melted rapidly, in geological terms, over perhaps a few thousand years, exposing rock to extreme weathering under the supercharged greenhouse atmosphere and depositing the distinctive cap carbonate layers that geologists find immediately above the diamictites. The biological consequences of Snowball Earth are still debated, but they were clearly profound. Complex multicellular life, the kind that would eventually lead to the Cambrian explosion, emerged in the Ediacaran period immediately following the final Snowball Earth episode approximately 580 million years ago. Whether the extreme environment of Snowball Earth acted as an evolutionary bottleneck that concentrated survivors in refugia under equatorial sea ice, creating the genetic diversity that subsequently exploded in the Cambrian, or whether the chemical changes associated with the thaw, the massive influx of nutrients from newly exposed rock, provided the metabolic and ecological opportunity for complexity to emerge, is an active area of research. What is clear is that the timing is not coincidental. The emergence of complex life on Earth was not a smooth, gradual process stretching back to the origin of life. It was a punctuated event, concentrated in time following the most extreme environmental perturbation in the past billion years of Earth's history. The Great Oxidation Event, occurring approximately 2.4 billion years ago, represents an earlier and equally dramatic planetary transformation, one caused not by cosmic or geological forces alone, but by life itself. For the first 2 billion years of Earth's history, the atmosphere contained essentially no free oxygen. The early atmosphere was dominated by nitrogen, carbon dioxide, water vapor, and smaller amounts of methane, ammonia, and other reduced gases. Iron in the ocean existed primarily in its reduced dissolved form, ferrous iron Fe2+. Life during this interval was entirely microbial and entirely anaerobic, around 2.7 to 3 billion years ago. A lineage of photosynthetic bacteria, the ancestors of modern cyanobacteria, evolved the capacity to split water molecules using sunlight, releasing oxygen as a byproduct. This was, in retrospect, one of the most consequential biochemical innovations in Earth's history. Cyanobacteria began producing oxygen at a scale that, over hundreds of millions of years, exceeded the capacity of oxygen sinks, the chemical reactions that consumed oxygen, particularly the oxidation of dissolved iron in the ocean, to absorb it. Around 2.4 billion years ago, the oxygen that had been accumulating in the ocean and reacting with dissolved iron crossed a threshold, and free oxygen began accumulating in the atmosphere. The consequences were catastrophic for the organisms that had been living in the anaerobic world. Free oxygen is a highly reactive chemical, toxic to many metabolic pathways that had evolved in its absence. The Great Oxidation Event killed the vast majority of anaerobic organisms on Earth, the largest mass extinction in the planet's history, though one largely invisible to the fossil record because the affected organisms were microbial and soft-bodied. The survivors were those capable of tolerating oxygen, or those that retreated into anoxic refugia, the deep ocean, sulfur-rich sediments, the guts of later multicellular animals, where they persist to this day as the anaerobic bacteria and archaea of modern ecology. The iron-rich sediments produced by the Great Oxidation Event, the banded iron formations that now constitute major iron ore deposits worldwide, including the Hammersley Basin of Australia, the Superior Iron Range of North America, and the Kursk magnetic anomaly of Russia, represent the chemical signature of this event. The direct record of the transformation of the ocean's iron chemistry as oxygen first appeared in quantity. Mining these ancient Precambrian iron formations today, we are in a sense extracting the metabolic waste product of ancient cyanobacteria, 2.5 billion years old, that fundamentally altered the chemistry of our planet. The Great Oxidation Event also had profound climatic consequences. Methane, a powerful greenhouse gas that had been produced by methanogenic archaea in the anoxic ocean and accumulated in the atmosphere, was rapidly oxidized to carbon dioxide as oxygen levels rose. Carbon dioxide is a less potent greenhouse gas than methane, and the net effect of replacing atmospheric methane with carbon dioxide was a dramatic cooling, possibly contributing to one of the earliest snowball Earth events. the Maganian glaciation at approximately 2.3 billion years ago. These interconnected catastrophes, the Great Oxidation Event triggering a glaciation, the glaciation eventually thawing in a CO2-driven greenhouse, the subsequent stabilization of the oxygen-rich atmosphere, illustrate the profound interdependence between life and planetary geochemistry. Earth's atmosphere is not a passive backdrop to the story of life. It is a product of life, maintained by life, and fundamentally altered at multiple points in history by evolutionary innovations in the microbial world. The oxygen in the air you are breathing right now is the accumulated waste product of cyanobacterial photosynthesis produced over the past 2.5 billion years. The nitrogen that makes up 78% of the atmosphere is largely the product of microbial denitrification, the regulation of atmospheric carbon dioxide, and with it the long-term temperature of the planet, is maintained by the combined action of geological processes and biological carbon cycling. This interdependence is what makes Earth's story different from the stories of Mars and Venus, all three planets formed from similar material in the same region of the solar system. All three had liquid water on their surfaces in the early solar system, but only Earth developed complex life, and only Earth maintained habitable conditions for long enough for that life to develop the extraordinary complexity it has achieved. The precise reasons for Earth's uniqueness, whether it is primarily the planet's size, its distance from the Sun, the presence of a large stabilizing moon, the particular combination of geological processes that regulate the long-term carbon cycle, the timing of the Great Oxidation Event, or some combination of all of these, remain active areas of research. The answer matters not only for understanding Earth's history, but for understanding how common or rare habitable planets are in the universe, and therefore how often life arises and how often it achieves complexity. The rocks beneath our feet contain the complete record of this experiment. From the earliest Archean sediments, preserving the chemical signatures of the first life, through the banded iron formations of the Great Oxidation Event, through the diamictites and cap carbonates of the snowball Earth episodes, through the Cambrian explosion of complex body forms, through the great extinctions and radiations, through the rise and fall of successive dominant groups, to the thin layer of chemically anomalous sediment being deposited right now on continental shelves and lake beds around the world. The record is there, incomplete and imperfect as all records are, but readable by those who know the language. Learning that language, understanding the timescales involved, the mechanisms operating, the forces that have shaped this planet across 4.5 billion years of history is one of the most important things that geology offers to anyone who wants to understand what kind of place this is and what kind of future it might have. Not because the knowledge is comforting. Much of it is not. The planet has been through catastrophes that dwarf anything in human experience, and it will go through more. But because understanding where we are in the timeline, understanding the forces that operate on timescales far longer than any human civilization, is the only basis on which rational decisions about the long-term future can be made. We are a geological force now, that much is established. The question of what kind of geological force we will be, whether a transient anomaly that leaves a thin chemical layer in the rock and disappears, or the beginning of something genuinely unprecedented in Earth's 4.5 billion year history, is still being answered. The answer will be written in the rock, as all answers eventually are. The planet is not finished. It has barely begun. And neither, if we understand what that means, have we